So today we are going to start studying concurrency, first from LockBased Concurrency. So the part name, which is Search for Safe API, and its meaning will become clear in the course of doing this slide. Okay, so let's start with LockBased Concurrency. But as a context, I'd like to introduce a shared memory concurrency as a concept before going into LockBased Concurrency, because it will be the context of all the concurrency we will learn in this course. So we assume that there are multiple threads in our program, and the multiple threads are sharing the same memory at the same time. So for example, there are thread 1, 2, 3, and blah blah and n, and they are all sharing the memory. So you can see that it is a little bit simplified view from the existing physical CPUs because they are caches or they are store buffers and all the kinds of complex things inside the actual implementations of the CPUs and memories and the system. But for the purpose of this class, for now, let's assume that we only have threads and they are sharing memory, and no other details will be evident at this moment. But later, maybe caches and other kinds of optimizations, they play a key role in understanding concurrency, so we will learn them later. But for now, let's focus on threads and memory. So this is the model of concurrency we are going to use, which is shared memory concurrency, because multiple threads are sharing the same memory at the same time. So here, a thread is basically an agent that is executing its own program. For example, usually it is a program with a program counter, and program counter is constantly increased, and the current instruction is executed in this thread. And the thread has a local storage that is usually called register or register file, and it is updating the registers on its own, and from time to time it is accessing the shared memory that is located in the stack or a heap in the usual nomenclature from architectures and operating systems. And yeah, it is requesting a read and write to the shared memory, and it will get responses from the shared memory. And in the course of doing so, it is executing on its own, and maybe it will execute some I/O so that the effect of this thread can be visible to the outside world. So this is basically a thread. So if we already took courses on operating systems, you may well know all these concepts, but I am reiterating these concepts here because I want to focus on some aspects of those ideas. Here, the idea I want to stress for thread is that it is an agent. It is agent that is accessing the shared memory or shared resources. On the other hand, shared memory is a resource. It is a shared storage resource of data. And data is written to this memory and read from this memory. So as a result, it is a resource, and it is shared among multiple threads. I want to stress that aspect of this shared memory. Okay, this is the context for lock-based concurrency and lock-free concurrency we will learn later. But maybe it will not be dealt with in this class, but there are other kinds of concurrencies as well. So this picture only captures the concurrency inside CPUs and memory, but there are shared memory concurrency or other kinds of concurrency among CPUs, not only CPUs and memories, but also accelerators like GPUs and FPGAs, or even the emerging class of persistent memories, like Intel Optane DC memories or ARM's upcoming persistent memories. Or even we can think of concurrency among multiple computers, basically. If multiple computers are attached to a single network and they are sharing some resources like databases or some caches, then you can think of it as a concurrent system, and you can analyze those distributed nodes in distributed systems as concurrent objects. But for now, let's focus on just memories and threads. So this is the context for our study for now. Okay, now let me introduce LockBased shared memory concurrency. So the lock-based means that at any moment, a single memory location is accessed by only a single agent. So that means that in shared memory, multiple threads are not accessing the same location at the same time in lock-based concurrency. So this is basically the meaning of these lock-based things. Okay, it corresponds to the easy concurrency I introduced in the previous lecture. And this is, as I said in the previous lecture, the main benefit of this is simplicity. So we basically kill all the concurrency, all the interesting concurrency that is shared mutable accesses to the same resource. So as a result, it is simple. Only one agent is accessing the resource. There's no actual concurrency. It's simple. However, the disadvantage of this approach is that it is possibly and quite often inefficient for our purposes because we kill all the concurrency and only one agent can access a single resource. As a result, we cannot parallelly execute multiple agents or multiple threads at the same time. So it is the pros and cons of this lock-based concurrency. But anyway, we start with this lock-based concurrency. It is simple, and we are going to look into lock-free concurrency later, after we master the concept of this lock-based concurrency. The major mechanism to achieve or to program this lock-based concurrency is, unsurprisingly, locks. And lock is an object for which only one thread holds the lock. So lock is basically an object, just like in the object in front of the door. Only one agent can hold the lock. If it is held by an agent and another one is trying to get it, it should wait for the other to finish using the lock. And it is effectively removing all the concurrency. So here's an example. Here, let's say that this is two threads, and this bar, double bar, is meaning thread separation. And there are left threads and there are right threads. And let's assume that these big letters are shared memory locations from now on. And these small letters will be registers, agent local or thread local registers. So this program is basically reading from X and adding it to 1, and then assigning the new value to the X again. At the same time, the right thread is doing the same thing. It is reading from X and then adding 1 and then storing it to X again. And also, as a convention, let's assume that all the shared memory locations are 0 at the beginning of the execution. And you may guess that, or you may argue that, at the end of the day, X should be 2, because it is incremented in the left thread, and it is incremented also in the right thread by 1. So as a result, X should be incremented by 2 times, and it should be 2. However, this reasoning is broken, and it actually doesn't happen. It actually doesn't hold in the real world systems, because unfortunate interleaving of the threads executions may produce, for example, X equals 1. Let's see why. So suppose that these threads are executed in an interleaved manner. That means that they are executing one instructions at a time, and they non-deterministically take turns and execute their own instructions. And suppose in an execution, this left thread is executing the first instruction, that is reading 0 from X and assigning 0 to R1. And then let's assume that the right thread takes turn, and it is reading 0 again from this X. And now the left thread takes turn and assigning 1 to X. And then the right thread takes turn, and maybe it is the case that X is assigned 1 again. So X is read as 0 in 2 threads, and it is assigned 1 in two threads, in both threads, in this particular scheduling of instruction executions. And if it is the case, it may be the case that x is not 2 but 1 at the end of the execution. So this anomaly, or this unfortunate non-determinism, arises from the fact that this x, which is a shared memory location, is actually accessed in a shared mutable way, because they are accessing the location at the same time, and they are actually modifying the content. So it is a shared mutable accesses to the same resource, and it causes the problem. It is beyond the reach of our thinking or our imagination of how this program should work. So in order to remedy this, we need to protect the accesses to the X. In order to do so, the easiest way to do so is inserting a lock. So let's say that L is a shared lock that is shared among the two threads, and L has two interfaces, two methods basically. The first one is acquire, that is acquiring a lock when it is not held, and the other API is release. So if you hold a lock and then you release this lock, then you're no longer holding the lock. Okay, now in the presence of this protection, acquire and release, the unfortunate interleaving does not happen, because let's say that the left thread execute the first instruction here and acquire the lock, and then it can read and write to the location X. But if this thread is acquiring a lock and it holds the lock, the right thread cannot enter into this line, because it should wait for the left thread to release the lock. It just waits for it to be released at the first line. The acquire function is not exiting until it successfully acquires the lock. And as a result, it should be the case that all the access to the X by the left thread should happen before all the access to the X in the right thread. And as a result, our imagination or our intention actually holds. The X should be 2 at the end of the day always, because lock prevents such unfortunate interleaving. And lock is such a useful construct that allow us to do such a reasoning. Since only one agent is accessing a single resource at the same time, we no longer need to reason about unfortunate interleavings and the non-determinisms that is arising from these interleavings. Okay, so far so good. And as I said, it has two APIs, and additionally it has one more API, try acquire. And as I said, acquire blocks until acquiring the lock. It just waits for other threads to release the lock. And try acquire returns whether a lock is acquired, and it may return false when another thread already held a lock, and it immediately returns false. Oh, I tried to acquire the lock, but I failed because other threads has acquired it. So I didn't acquire the lock. Or it may return true. That means that I successfully acquired the lock. The third API is release, that is releasing the lock that I have already acquired previously. So these are the low-level API of these locks, and this is the most important API of all concurrencies. Lock is the most important object in all concurrent programming, and this API is the most important APIs of these locks. Okay, so far so good. If you use this API well, then it is guaranteed that there is no longer shared mutable accesses to the resources, and it may be easy to reason about concurrent programs. But there is a pitfall. The pitfall is that this API is really extremely error-prone. It is really easy to misuse this API so that the system can hang, or the system can be broken. The invariant can be broken. For example, if you don't write release here, then the system will hang because this thread cannot acquire the lock. On the other hand, if you forget to insert the acquire here, then the invariant x equals 2 may not hold at the end of the execution. So you need to somehow very intelligently insert those API invocations, and only if you successfully inserted those very well, the system will work as you intended. But it is extremely error-prone for two reasons. The first reason is that it is from this API, it is somewhat coincidental, or it is somewhat lucky to protect X using L. I mean, there is no explicit relation in the code between L and X. We, the programmer, just know that, oh, X is protected by L, and as a result, we can safely use X in this code. But there's no such explicit marking of the relationship between L and X. And as a result, it may be the case that we are acquiring a wrong lock that is not meant to be protecting the X. Or we may use different resources that is not intended to be protected by this log L. If that happens, all the invariants are broken, and this unfortunate result may pop up, even though you use locks. The second challenge is that the second reason why the API is error-prone is you need to match acquire and release very well. You should not forget about releasing the lock. You should not forget about acquiring the lock at the same time. And you should release the lock you have already acquired. If you are releasing different lock, then it is problematic. Okay, for these reasons, this API is, in my opinion, really error-prone. I know that a lot of programs like Linux are implemented this way, and very well. Linux code is very well maintained, but it is still very error-prone, and is for beginners and is for those who are working on large code base. Large code base usually have bug when the program is written in this way, because no one is understanding the entire code base, and the invariant becomes extremely complicated. And if API is such low level, we cannot somehow statically guarantee that the entire program is well written. And these challenges, this API problem, is particularly more problematic for concurrent programming. And the reason is that the programmer needs to be concerned with the API all the time, and it is costing high cost. And it is especially so for concurrent programming, because concurrent programs usually have much more complex invariant than the sequential programs. And as a result, the programmer needs to take into account this complex invariant all the time. And it is causing very high cognitive load to the programmers. And still, even though programmers are very much concerned with these bugs, usually there will be remaining bugs in large systems. So I saw concurrent programs of millions or 10 millions of lines of code, and they usually have a lot of bugs because no one is understanding the entire invariant. And this bug is difficult to test as well, because usually such a bug, such a hidden bug pops up once every, for example, million times or billion times. So testing coverage, it is difficult to achieve high test coverage for those kind of concurrent programs. And that's the reason why this error-prone API is more problematic for concurrent programs. Okay, that's the reason why we want to use HighLevel API for those locks, because we want easy to use and always API. So if an API, a lock API, is always safe and it is bulletproof, then it is much easier for programmers because programmers don't need to worry about safety no longer. If a program is compiled using this HighLevel API, then it is okay. The compiler guarantees that this lock will work as I intended. And this is a great benefit. I mean, if there is no such a benefit, programmers should be concerned about the invariant all the time. But if compiler guarantees this invariant, then you can forget about this. You can just forget about this and use HighLevel API. And automatically there will be no bug. So in particular, we want a HighLevel API that is automatically matching acquire and release functions. And also, the HighLevel API should relate a lock and the corresponding inner resource explicitly. For example, the relationship between L and X should be explicitly marked in the program. And as a result, there is no confusion about which lock protects which data. Okay, as I said, this kind of HighLevel API is low cost and it introduces less bug because all the bugs will be automatically eradicated thanks to the HighLevel API and the compiler. Okay, and for locks, already there are many kinds of HighLevel APIs, and the most prominent one is from C++, and its ability to do resource acquisition is initialization, or RAII. And the high-level idea of this API is the two things. So in order to automatically matching acquire and release invocations, we are introducing a RAII type, which is a lock guard. And when you acquire a lock, then it returns a lock guard instead of just return nothing. It returns a lock guard, and when this lock guard is destructed, the corresponding lock is automatically released. So as far as this lock guard is there, and if it is not intentionally somehow forgotten about, then the corresponding lock that created the lock guard is automatically released, and acquire and release function is automatically matched. That is basically the intention of this lock guard. And if you don't understand what I'm saying, you probably want to search for this RAII, or resource acquisition is initialization pattern. Okay, and the second thing, in order to relate a lock and a resource in an explicit way, we introduce a new type that is lock and T, and this is basically a pair of a lock and the data T, and it is explicitly marking that a lock is associated with data of type T, and as a result, we are no longer confused with which data is protecting with which resources. So let me show you the example of these two. So here is a API of the lock guard, which is in the standard C++. So here, let's just think that mutex is a kind of lock. So it is a lock. And at the beginning of this function, this is called in main function. The main function is creating two threads, and each thread is executing the save increment function. And it is then the main thread is then waiting for the T1 and T2 to be finished, and later it is printing the value here. And main thread is launching a new thread that is executing save increment, and inside the save increment that is executed by each thread, it is acquiring a lock here by creating a lock guard. And this is the name of the lock guard, lock, and it is acquiring the lock from this mutex. And this is an RAII type, and it signifies that I am now holding the lock mutex here. GI lock is acquired by me, and this is the proof that I acquired it. Lock guard is a proof that I have acquired the GI mutex. And after that, I am incrementing or accessing the GI, which is a shared resource. But it is okay because I acquired the lock GI mutex. And now, at the end of the day, I'm returning from this function, and this lock is destructed here at the end of the function. And what is interesting here is that when lock is destructed, GI mutex is automatically released. So that is basically the idea behind RAII. You initialize this resource, lock guard, using an initializer. And at the end of the day, when it is destructed, you are automatically running some code. In this case, it is releasing the lock. In this way, we cannot forget about releasing the lock because this lock guard is automatically releasing the lock. We cannot forget. We cannot force this to not to release the lock unless we are doing something strange here. Okay, the second idea is relating data and a lock. And as I said, the benefit is that it is mandating, it is making explicit which data is protected by which lock. And the type looks like this. The lock type is consisting of two data, which is a row lock, the lock type of the lock that has acquire and release functions, and the data type. And if you acquire a lock by calling this lock function, then you are basically creating a lock guard. But before that, you are acquiring a lock, because lock guard means that you acquire the lock, so you need to actually acquire the lock. And after that, you return the lock guard. That signifies the fact that you have acquired it. So far so good. And when you have a lock guard, then you can dereference the inner data, because it is there is a proof that you acquired the lock. So you are legitimately allowed to access the inner data. That's the reason why we implement this operator. So when lock guard is used, it can be automatically transformed into the reference to the data, inner data. So it is possible because we explicitly related lock and data. That's the reason why we can dereference from this lock guard into the data. And now at the end of the day, after finishing dereferencing the data, we can release the lock by destructing this lock guard. In the destructor of this lock guard, we are releasing the lock here. So as a result, we are automatically releasing the lock. So in summary, this API achieves the two goals at the same time, matching acquire and release at the same time, and furthermore, it is explicitly relating a lock and a data. So far so good, and it is quite a good API, and it's the best API we can think of inside the C++ programming language, but actually it is not 100% safe. It is safe-ish API, but still there is a huge case for which we can break the system using this API. Let's what's happening here. So let's see that there is a lock of type lock of integer, and you acquire the lock here and get the guard here. And suppose that you dereference the guard and get the pointer to the data. So it is okay. It is allowed in C++ because you acquire the guard, and the guard can be converted into the pointer to the data. Now suppose that data guard is dropped here or destructed here, and lock is automatically released. But the problem is that the pointer data underscore PTR is still there, and we can still dereference the pointer here. But if it is the case, it is very much unsafe. It breaks all the invariant that is provided by the lock type. Because even it can access the inner data without holding the lock, because the lock is already released here. So maybe it is the case that other threads has acquired the lock and accessing the same data at the same time. Then the unfortunate interleaving may happen from there. It is no longer as intended. So as I said, the root cause here is that this pointer to data is leaked after the guard is destructed and lock is released. So data PTR is leaked here after the guard is dropped, and that's the root cause. Conversely, we have to mandate that data pointer should not outlive the lifetime of this data guard. When data guard is really dropped and the lock is released, data pointer should no longer be used from now on. But it is using that, and the API actually allows that. You may think that it is a pedantic approach to argue the unsafety of this API. So you may say that this doesn't happen in the real world. But in my experience, it is actually happening in real world, in production code. And it causes a lot of troubles. The reason why it happens in the real world code is that the programmers are doing whatever they want if it is allowed. If you can get a pointer out of this data, they do for later purposes. But probably for a goodwill, I get the pointer here and use this pointer before the guard is dropped. But later, they forget about this invariant and they use the pointer after the guard is dropped. So it is really difficult to guarantee the API is used as intended if there are a lot of programmers working on a big code base. So if this kind of API is, into my eyes, very much error prone, and it actually causes the trouble in the real world production code. So the solution I'm proposing here is using the program language Rust's type system based on ownership and lifetime. So Rust is specifically designed to avoid all such problems like this. So this is basically a lifetime problem. The lifetime of data pointer should not be longer than the lifetime of data guard, and it should be somehow guaranteed in the type system. But that is basically the purpose of the Rust type system, preventing the lifetime problems of the libraries and the programs. So in Rust type system, we can actually guarantee that. So that's the reason why Rust can solve such problems. So that's also the reason why in this course we are going to use Rust instead of the C++ that is most widely used in concurrent programming. Because I believe that Rust type system is very good API. It provides very good API for learning and implementing concurrent libraries. And by learning this, I believe that you can be a better concurrent programmer. Even though you are going to use C++ in the future for concurrent programming, learning Rust and learning concurrency with Rust will be very much helpful. And here is a safe implementation of lock with a safe API. And the safety of this API is actually proven in a research paper. And this API will be discussed in a later phase of this course. Okay, so this is basically the why this API is unsafe in C++, and I mentioned that this API can become safe in Rust. And before delving into the safe API in Rust, we really need to discuss and study Rust first. So in the next video, we are going to study Rust as a crash course, and then go back to the concurrency and continue to study the LockBased concurrency and its core concept and its APIs.